Forces. So we're going to be looking at a number of different forces, and they get the labels of intermolecular force or intramolecular force. So whether it's inter or intra. So inter is talking about between two different molecules, specifically if it's intermolecular, and intramolecular is within a molecule. So this gets broken up into sort of these two groups here. So if we think of intramolecular, even though ionic compounds aren't molecules, essentially the force that holds them together does get the label of intramolecular. It's the electrostatic charge of the ions, and that's what holds ionic compounds together. A covalent bond, so let's imagine this was two hydrogen atoms bonded together with their shared pair of electrons between them. The name fits perfectly for that one. It is the force within the molecule that holds those two nuclei together. That is a covalent bond. And metallic bonding is what holds metal atoms together into a clump of metal. And again, it's not really a molecule, but the idea is that it's within this type of substance here. So that's where the intra part comes from, even if the molecular part doesn't quite fit for all of them. Then the intermolecular force is generally when you have two different particles, the force of attraction between those two particles. So imagine any combination of two particles, and if they are attracted to each other, that would be a particular type of intermolecular force. Now just name the particle, and then you can come up with the name of the force itself. If it involves an ion and a dipole, we call it ion-dipole. If it is a dipole attracted to another dipole, we call it dipole-dipole. If that dipole is because of hydrogen bonding, which we'll talk a little bit, we call it specifically hydrogen bonding intermolecular force. And then we're going to talk about these induced forces a little bit later with London forces as well. So here's what we're going through. And essentially, if you look at the energy, which is the strength of these types of bonds, it varies, but what you should realize is there is sometimes a very huge range within the strength of these bonds. So if we were to graph those numbers there, essentially we end up with the different type of bonds and the range of their strength. So ionic bonds could have a huge amount of energy required to separate them, but they could also have a not quite as much energy. Covalent bonds, again, they have high and low, so different strength of covalent bonds. And what you should see here is that sometimes there's overlap between them. So if we looked at an ion-dipole bond, sometimes they're quite strong, and sometimes they're actually stronger. It's not very straight. Sometimes they're actually stronger than the ionic bonds. So we may, when comparing whether an ionic bond is stronger than an ion-dipole, it kind of depends on which ones you're talking about. A lot of them are stronger, but then there's some that are not stronger. So it is very much specific as to which type of atoms are making up these forces. So bond polarity is one of the things that we're going to be using in here. And so we have the bonding continuum. And if the electronegativity difference between the two atoms is calculated, we can figure out what label we could put on the bond. But what's more important than the label itself is how big of a difference is there. If there is no difference in the bond, then the two atoms are sharing those electrons perfectly. As you go from 0 to a higher number, the sharing becomes less equal. Now we like to label things and give them names, and so we have decided that if it is above 1.7, we're going to give it the name ionic. If it's below 1.7, we're going to give it the name covalent, of which it could be not that equal sharing, or it could be more equal sharing. Or if it's 0, it's perfectly equal sharing. And so again, the labels are less important than what the number is and what the number tells you. The shape of the molecules themselves will determine the polarity of the molecule. So realize we've got two different things here. We've got bond polarity and we've got molecular polarity. Two very different things. Bond polarity is super easy to figure out. You just find the electronegativity difference. Molecular polarity is going to be more complicated because you need to know the shape of the molecule. and then the interactions that happen within the molecule, how the dipoles act on each other, are going to sum up to give you whether or not the molecule itself is polar. So again, just to try to get you to think more beyond those labels, if we actually looked at the percent ionicness, so essentially how unequal the sharing of electrons is within a bond, we can look at 0 going up to very, very unequal. If we were to graph this based on the electronegativity difference, we can see that obviously if the difference between the two atoms' electronegativity was 0, because they're the same atom, then obviously it's going to be perfectly equal, and that bond is not going to be very ionic at all. There's not going to be any charges on those atoms. But as we move from an electronegativity difference of 0 up to, let's say, I don't know, 1.7, the percent ionicness of the bonds becomes greater. And so essentially that 1.7 cutoff is somewhere around 50% ionic. So essentially how large are the charges becoming on those atoms that are sharing the bond based on how much more electronegative one of the atoms is compared to the other. The takeaway is though that this is pretty linear, right? It's not like it jumps in steps. And so the difference between a really polar covalent bond and a not so ionic bond isn't very much. There's no steps in this graph here. And so again, more so than what the label tells you, think about what that electronegativity difference means and realize it's a pretty gradual linear relationship between the difference in electronegativity of the bonds and how unequal the sharing is. There is no real cutoff or steps along the way, even though we say 1.7 and we say 0.5 arbitrarily to give them labels just to make our lives easier. It doesn't give us all the details though. So bond polarity, super easy. Find the electronegativity difference between the two atoms and you will be able to say how polar the bond is. Molecular polarity, you have to be able to find the bond polarity first, and then you have to factor in the shape of the molecule. So 2 steps, and once you've done that, then you can come to a conclusion and decide, okay, is the molecule polar or not? But realize just because you have polar bonds doesn't mean the molecule is going to be polar. The shape can affect that. So, for example, CO2 does have polar bonds, but is a non-polar molecule, whereas water, which also has polar bonds, is a polar molecule. And it has to do with the interaction of the dipoles within the shapes. So we can represent these dipoles with an arrow. We do a positive on the tail of the arrow and a pointing towards where the negative is. So since hydrogen is less electronegative, let's look at the water first. Hydrogen is less electronegative than the oxygen. The oxygen hogs electrons from the hydrogen, and this gives the oxygen a partial positive charge. Not so much that it's an ionic charge, it's that the oxygen doesn't take the electrons from hydrogen, but it does leave oxygen with a negative charge and hydrogen with a positive charge. Same thing on the other end. If we were to look at the total of the dipoles within the molecule, we can kind of imagine that these dipoles are both pointing towards the oxygen. They kind of cancel each other out a little bit left to right in the way that this is drawn, but the overall dipole of the molecule points towards the oxygen. So we end up with a sort of a negative charge over at this side and a positive charge over at this side. So this is what we mean by this molecule is polar. We have one side that has a different charge than the other side, or at least partial charge. With carbon dioxide, though, the dipoles point away from the carbon towards the oxygen, but they are exactly opposite from each other. And so one end is going to be negative, and the other end is also going to be negative. So there is no difference in charges between the two ends. Essentially, the dipoles cancel out. The molecule does not have one side that's different than the other, so it is a non-polar molecule. So to determine the polarity, you got to be able to draw the Lewis structure first and figure out what sort of bonding you have and how many atoms you have around it, where the electrons are. Look up the electronegativity for each bond. Draw the partial charges in the dipoles. figure out what the shape is, and so make sure you've got the correct shape based on your VSEPR knowledge. And then you can say, okay, do the dipoles cancel out or not? Essentially, if the molecule's symmetrical, they're going to cancel each other out. If they're all pointing in the same direction or they're all pointing opposite directions, you don't end up with one side being different than the other. And so that is going to be a non-polar molecule. But if they add together in some way, and one end of the molecule ends up having a different charge than the other, and we're talking partial charges here, then it's going to be a polar molecule. Intermolecular forces. So these are the forces between the particles. So once you know what's going on within the particle, if it's a molecule, figuring out whether it's polar or not, then you can talk about the intermolecular forces. So the forces between the molecules. These tend to be weaker. Again, there is some overlap depending on what the combination happens to be, but are generally weaker than the intramolecular bonds. And this is why when you take a substance that's made of molecules and you heat it up, you don't break apart the molecules because the molecules are held together with intramolecular bonds. They don't want to be broken apart, or it takes a whole lot of energy to do anyways. But when you boil a molecular substance, you're breaking the intermolecular forces, the forces that hold the different molecules together. So think intermolecular forces. If you have one particle here and one particle here, the force between them, that is the intermolecular force, whereas an intramolecular force is just the force holding the particle itself together, much harder to break in most cases. So these help to explain the properties of the substance, because if you have a substance, you're going to have a whole bunch of these particles, let's say, and they're going to be attracted to each other within that substance. So there's going to be an intermolecular force holding that substance together, and that will tell us what sort of properties that substance is going to have. If they're really easy to break, for example, it would have a low melting point. So we're going to look at 5 of these intermolecular forces. First one, what's called a London force or a dispersion force, or a London dispersion force. This is the attraction of one atom's or molecule's electrons by another atom's nuclei. And again, you focus on the atom because obviously a molecule is going to have atoms in it. And so you think of the one molecule's atom definitely has electrons around it. The other molecule's atoms definitely have nuclei in them. They have opposite charges, so there's going to be some attraction there. And so imagine if this guy here, and whether it was connected to some other atoms and whatever, it doesn't matter. The fact that whether it's part of a molecule or it is just a lone atom, the same force is going to exist. So its electrons, which have a negative charge, they're definitely attracted to the nucleus. They're not going to leave the nucleus. But the other atom also has a nucleus with a positive charge. So essentially that attraction between those two atoms, which may be part of other molecules, that attraction is called London dispersion forces. It's relatively weak because, again, the electrons are attracted to their own nucleus quite strongly, and their attraction to the other atom's nuclei is going to be there, but is going to be relatively weak. However, if you have a big molecule over here with lots of atoms around it, there's going to be more of that attraction the bigger the molecule gets. And so these atoms end up being more and more attracted if there are more and more of them. And it also depends on the size of the atoms as well. Bigger atoms are going to have more London forces associated with them. So looking at the effect of London forces on boiling points, if we look at these substances here, a carbon with 4 hydrogens around it has a total of 10 electrons. Its boiling point is negative 164 Celsius. So we're working with Celsius here. When you go to silicon with 4 hydrogens around it, you're dealing with a bigger central atom. There's more protons and electrons around those atoms, and the temperature is higher. It's at a higher boiling point than the methane does. And the reason is because even though they're both similarly shaped, this silicon with 4 hydrogens is a bigger molecule in terms of the central atom has more electrons and protons, same number of atoms, but more electrons and protons. So when you have a gazillion of them sitting in a container together, there's going to be more attraction between those molecules than there would be with the methane. And then the germanium with the hydrogen is an even bigger central atom, which has even more protons and electrons. and therefore its boiling point is even higher still. And you can see the trend here with a tin as their central atom. Again, more protons, more electrons, and an even higher boiling point. So the more protons and electrons you have, either because you're dealing with bigger atoms in this case, or if you had a molecule which had more atoms, the same effect would happen. More electrons, which come with the accompanying protons in the nuclei, means more London forces, which results in a higher boiling point. So, for example, if we were to look at ethylene, we have a carbon bonded to a carbon with a double bond, some hydrogens around there. This one here has distinct units with 4 hydrogens and 2 carbons. If you look at polyethylene, so imagine the same sort of setup. We don't have a double bond there, but instead we have more carbons attached, and it's going to keep going. That's hence the poly part. And it is going to be a bigger molecule because it's got more of these carbon hydrogen attached to it, making it a bigger chain. If you looked at the molar mass of them, whatever ethylene is, you take that and you're going to multiply it by however many carbons are in the polyethylene, or whatever poly denotes, it's some large number. And so the boiling point of ethylene is super low. The London forces aren't particularly strong. So if I had another ethylene here with a carbon double bonded to another carbon and some hydrogens on it, if I had another one, the force between them, so the attraction of one ethylene to the other, is pretty weak. But when I have polyethylene, I've got this giant molecule, lots of carbons in it, and hydrogens. So some big molecule, there's lots of opportunity for the atoms in one of these molecules to be attracted to the atoms in the other one. So much more opportunity for London forces, and therefore a much higher melting point. So take a look at these guys. Let me put the first one up here. So this is, what is that, tellurium or something like that? So yeah, tellurium with 2 hydrogens on it. 54 electrons. It has a boiling point, so here it is right here. It has a boiling point of -2 degrees Celsius. If we go to the next one in the family, selenium, where we've got a smaller atom here, less electrons, and so fewer London forces, so its boiling point is going to be lower. It's a greater negative number, it's lower. So as we see, as we move from the lower to the higher, in terms of on the group here, which in terms of electrons, if they're low down on a group, they have lots of electrons and protons. As we move to smaller and smaller, and so here's sulfur with 2 hydrogens, the boiling point is getting lower and lower. So it's easier and easier to separate a small molecule than it is to separate large molecules apart from their friends. Remember, we are talking about intermolecular forces. We're not breaking up these molecules, we're just separating them from their friends. Now, this guy here with only 10 electrons, you'd assume based on this pattern here, this is a much smaller molecule. If we look at the pattern, we got -2, -40, -60, you'd figure, I don't know, maybe -80. Its boiling point is +100. So there's something else going on with this guy. And this is our next intramolecular force. So yes, London forces are important, but they're not the only force out there. Hydrogen bonding is an incredibly strong force that happens when hydrogen is bonded with nitrogen, oxygen, or fluorine. And so we're talking about a hydrogen bonded to a nitrogen, and again the nitrogen will be bonded to other things as well, a hydrogen bonded to an oxygen, or a hydrogen bonded to a fluorine. And I believe that this is just part of the molecule. There would be other bonds on the oxygen, there would be other bonds on the nitrogen as well, but we're just focusing on the hydrogen nitrogen, hydrogen oxygen, hydrogen fluorine. These guys here end up with such a large electronegativity difference because nitrogen, oxygen, and fluorine, the reason why these ones are important is because they're right at the top right hand side there. They've got a high, I don't want a delta, high electronegativity, which leads to the hydrogen and one of them having a high delta En. So essentially, we get a big dipole happening with each one of these, in that if the partner is nitrogen, oxygen, or fluorine, that partner is going to hog the electrons and it's going to leave hydrogen with quite a positive charge to it. That's a positive sign. In each case of it, and probably leave the other one, the nitrogen, oxygen, fluorine, with quite a negative charge to it. So this sets up a large dipole in each of these cases. So hydrogen can form these special hydrogen bonds when you've got these strong dipoles. So let's clean this up a bit. We have, in this case here, get a smaller pencil. In each case here, this is water. So the hydrogen is having its electrons pulled away from it by the oxygens, and the hydrogen bonding is not within the molecule. So don't confuse these guys here bonding with the hydrogen. It is what happens between one molecule and another. And so it is the force that exists between the two water molecules, not within the water molecule. That's an intramolecular force. This is an intermolecular force that exists between the molecules because each of the molecules has such strong dipole-dipole forces, and this is so strong that it actually gets the name hydrogen bonding. And so the attraction that's set up between this one strong dipole and this other strong dipole, that is called a hydrogen bond. This leads to several interesting properties of substances that can form hydrogen bonding, specifically looking at water. Cohesion and adhesion, so water is really sticky to other things that have charges on them. And so things like the vascular tissue of plants, the water is able to stick onto the cellulose of the plant because it has a very strong dipole, and cellulose also has dipoles in it, so it ends up adhering. I don't know if that's a word or not, but basically being attracted to other surfaces with charges as well. And cohesion is water sticking to itself. And so if you have a water droplet, if there's nothing else around for it to be attracted to, it sticks to itself really well because all the water molecules really like hanging out with each other because they have such strong dipoles. You end up with this cohesion properties of it, which is good for things like spiders and basilisk lizards, because the surface tension that happens specifically at the surface, because the ones at the surface have fewer water molecules to hang on to, the ones in the middle have got water all around them to hang on to, the ones on the surface just have to hang on to the guys underneath them and beside them, so they hang on really tightly, and therefore if you get going fast enough and don't put too much pressure on them, you can actually push down on the surface of the water without breaking these cohesive dipole-dipole, specifically named hydrogen bonding bonds. They also have the ability to dissolve other substances that are charged. So ionic substances, as long as the charges between the ions aren't so strong, they're able to break up those, and instead of interacting with their fellow ions, they interact with the water, because water also has quite a charge to it. And other polar molecules as well will be quite attracted to water because of the strong dipoles. High heat capacity, because again, water really likes to stick to other water molecules. If you want to get them moving relative to each other, it takes a fair amount of energy to force those bonds to move apart from each other. Looking at hydrogen bonding, the next step down from it would be dipole-dipole, and this is the same thing that's causing it. It's a difference in electronegativity, setting up a particular dipole within a molecule, and then another molecule also having a dipole in it. And if you have two dipoles, then one dipole will be attracted to the other dipole. And so if this is one molecule and that's one molecule, the dipole-dipole attractive force between the two of them is because one has charges and the other one has opposite charges, so they're going to be attracted to each other. It's not as strong as hydrogen bonding, but again, it really depends on the dipoles you're talking about, and really hydrogen bonding is a dipole-dipole force. It's just a very specific type. We give it its own name. So imagine you had hydrogen and chlorine bonding together to form HCl. You're going to get a dipole within that molecule. So if you take a container filled with this stuff, the two molecules are going to be attracted to each other, and there's a gazillion around, so they're going to be held together through dipole-dipole attraction. An example of this would be looking at tetrafluoromethane on the left here, and fluoromethane. So as you can tell from the name, the difference is whether it has 4 fluorines or just one and a bunch of hydrogens. So if it has 4 fluorines around it, you can imagine that the dipoles set up are going to point towards the fluorines, and you can check your periodic table, but fluorine being the most electronegative on the table, you know it's going to be the one that's hogging the electrons. So we're going to have partial negative charges all the way around the molecule, and since one end is not different than the other end, this molecule is going to be nonpolar. It is a much bigger molecule, so it should have more London forces, but when you look at the shape of the molecule, which is what you need to do to determine the molecular polarity, you can see that it's a nonpolar molecule. And if we look at fluoromethane, we have one of those dipoles happening. So this fluorine up here is going to be ended with a negative charge. These hydrogens here, not a whole lot of dipole going on. It's not an electronegativity difference of 0, but definitely that fluorine is going to be much more different to the carbon than the hydrogens are in terms of electronegativity. So that's where you're going to have your most amount of difference in charge. And again, a relatively small molecule, so not a huge amount of London forces. But if you look at the energy it takes to get this guy apart, this is at negative 78. Which is much higher, so negative 78, much higher than this negative 127. This molecule takes a whole lot more energy to separate from its friends because it has some polarity built into it. So this carbon ends up with a slightly positive charge, and if you had a whole bunch of them, they would have more polarity attracting each other, holding the substance together, than the tetrafluoromethane would. Next we have ion-dipole, and so again, if you take a positive or a negative ion and you have a dipole which has a positive and a negative side, the ion will be attracted to the dipole will be attracted to the ion because they have negative charges. Whether it's an anion or cation, a polar molecule is going to be attracted to it, and so we have this other type of intermolecular force. And again, that molecular name doesn't fit perfectly because obviously ions aren't molecules, but it is the force between a polar molecule and an ion. Then we have these induced forces. So these are the forces that aren't normally there, but can be there temporarily. So momentary polarization of something that's not normally polar. So you looked at oxygen, gas, it's a nonpolar molecule. However, if you move a polar molecule, so remember we have water here with a partial negative and a partial positive end to it. So if we move this close to it, just like when you charge a balloon and then you, with your hair, and then you stick it to the wall doesn't have a charge to it. But if you bring a negative something or other, a negative charge towards it, the negative charges, in this case in the oxygen, they're going to move over to try to get away from it. So they'll end up on one side, giving that side a partial negative charge, and they've left the other side, so it'll have a partial positive charge. So what we have is a temporarily induced dipole forming within the oxygen gas. Same thing can happen, so it happens with these polar molecules, but it can also happen with charged ions. They'll push or pull on the charges within nonpolar molecules as well. Just a quick note about the term van der Waals forces. You may have heard maybe in bio talking about van der Waals forces. You can sort of think of them as a group of some of these weaker forces. So they're referring to the weaker forces between substances, particles within substances. So things like dipole-dipole forces, induced dipole-dipole forces, and London forces. Those would fit into that particular category. All right, so again, we have our intramolecular forces and our intermolecular forces. The big difference is the strength of the force. The intramolecular forces, it's all kind of the same thing. It's all just particles being attracted to other particles. What's different is the type of particle we're dealing with. And again, because of the types of particles, we can have different levels of attraction. And so we give those different rankings different names. So ions are really attracted to ions. They have a strong force, so we've given them the name an ion or an ionic bond. Atoms within molecules are going to share electrons between them and be really attracted to each other in doing so through that bond, and so we give that a particular name called covalent bonding. Metals are held together quite well by that sea of electrons, so it tends to be a relatively strong force as well, so it gets its own name and we put it in this particular group. The weaker forces get put into another group, and they each get their own names based on the type of attraction that we have. But it all really is just forces of attraction between particles. All right, if we look at these three examples here, the first one we can see we've got some polar molecules and we've got an ion, and so we have polar molecules being attracted to an ion. So that is an ion-dipole force. This one here, we've got water and we've got methanol. And if you look at the formula for methanol, that should help out. We've got two really polar molecules, and they're so polar, in fact, they involve hydrogen and oxygen. And so each of those molecules have a hydrogen-oxygen dipole set up between them. And so this particular type of force between those molecules would be considered a hydrogen bond, a specific type of dipole-dipole attraction. If you don't have two molecules that are possible of doing hydrogen bonding, so chloroform here, it does have a dipole to it, and we have methanol again, it does have a dipole to it, but we don't have the two of them possible of forming really strong dipoles, and so we don't have hydrogen bonding in that case. We would just have dipole-dipole attraction. And there's the other one. If we have a non-polar molecule with a charge to it, a non-polar molecule and an ion with the charge to it, that ion can induce a temporary polarity in the non-polar molecule. So chloride ions and hexane molecules, they would consider the reason why they'd be attracted to each other, we'd call that particular type an ion-induced dipole. It could be also induced by a other dipole, so we call that dipole-induced dipole. And then if we have two non-polar substances, there is still going to be attraction between them. Weaker attraction, if you have more atoms, you get a stronger attraction there, but it's relatively weak, and so we call that London dispersion forces.